All right. Today we are going to continue on with the back end of Chapter 2. We're going to focus on measures of spread and the shapes of distributions. So the primary measures of spread are variance, standard deviation, and something that we call a z-score. So let's start up here with our sample variance and population variance. We denote a sample variance with the letter S and then squared, so S squared. And the population variance is denoted by the lowercase Greek letter here. So this is also squared. It looks like a 6 got ran over by a bus, but essentially this is our Greek letter for population variance. Oftentimes we don't know the variance. We have to use sample variance to estimate it. But in either case, our summation notation returns. In our sample variance, it is equal to the sum of the squares of the differences divided by the sample size minus 1. For population variance is equal to the sum of the squares of the differences divided by the total population size. Our sample standard deviation, we denote that by S. That's just the square root of the sample variance. And the population standard deviation is equal to the square root of the population variance. So if you're given one, you can get the other very straightforwardly. By definition, these all must be non-negative because of the squares. Now, I want to explain what's going on here. So the main difference between these two is their denominators. For population variance, we have capital N that denotes the entire population size. For sample variance, we have lowercase n to stay accustomed with sample size. And we subtract 1 from it. You might say, why? Why would we subtract 1? The reason why is because we're using it to estimate the population variance. So we're spending some of our sample to estimate it. And so that's why we have this n minus 1. Now you might ask, okay, fine, but what's going on in these numerators? I get this sum, but what are we summing here? Here's what we do. We take our sample and we compute the sample average, in the case of sample variance. And that is our x bar. We then take every single data point and subtract the mean from it. And so now we have a list of differences. We square all of those differences and then add them all up. That's what's going on in our numerator. And I will give you an example of that. With population variance, it's the difference between each data point and the mean. We do all those differences, we square each one, and then we add all those squares together. So let me give you an example. Suppose that our data point, we're going to use an overly simplified one, about as easy as we can. 1, 2, 3, 4, and 5. And let's assume that this is a sample. Well, the first thing we need to do is get our sample mean. This is equal to the sum of our data points divided by the number of data points, which is 5. So this will be equal to 3. Now what we need to do is get the squares to differences, and I recommend that you set up a table. So in our first column, we're going to have our data points, xi. So our data points are 1, 2, 3, 4, and 5. Now we need to get the differences between the data points and the sample mean. So that's going to be 1 minus 3. Our next one is 2 minus 3, because the 2 goes here. Then we have 3 minus 3. 3 goes here. 4 minus 3. And 5 minus 3. Since we're taking the squares of these differences, we're going to square each of these differences. And so this is our second column. So 1 minus 3 is negative 2. Square that makes it positive. That'll be positive 4. 2 minus 3 is negative 1. Square that, positive 1. 3 minus 3 is just 0. So square of 0 is going to be itself. 4 minus 3 is 1. Square that, it's 1. 5 minus 3 is 2. Square that is 4. Now, we need to add them all up. Because our numerator, we have to add everything together. So, 4 plus 1 is 5. Plus 1 plus 4, another 5. So, 10. So, our denominator is going to be 10. Finally, since this is a sample, we need to divide by n minus 1. So, in this case, we have 10 over 5 minus 1. So 10 over 4, 2.5 is the sample variance, or s squared. If you wanted to get the sample standard deviation, it would be the square root of s squared, because s is equal to square root of s squared to cancel it out. And if you rounded it to 3 decimal places, that would be about 1.581. So for this overly simplistic sample, we have a sample variance of 2.5 and a sample standard deviation of 1.581. When it comes to the exams, you will calculate either a sample or population variance, but you're going to have no more than 5 data points, so it won't be too overly bearing. If we have larger numbers of data points, then either the sample variance, sample standard deviation, population variance, or population standard deviation will be either computed for you or just straight up provided to you. So what I want to do is give you a practice problem. And for this one, I want you to assume that it is a population. I'm sorry. Assume it's a sample size. Let's make that larger. There we go. All right. We're going to go ahead and go over it. So again, we need to get our, let's zoom in a little bit. We need to get our sample average, our sample mean. This is equal to the sum of our data points. And we divide this by our sample size of 5. 3 plus 7 is 10. 8 plus 5 is 13, plus 7, 20. So we're going to have 30 over 5, which will be 6. Now we can proceed to our table. So first up, we need our data points, which are 3, 7, 5, 8, and 7. We now need to get the squares of the differences. So we're going to have 3 minus 6, 7 minus 6, 5 minus 6, 8 minus 6, and 7 minus 6. These are all squared. And now we get these values. 3 minus 6, negative 3. Square that, positive 9. That I don't know what is happening there. There we go. 7 minus 6 is 1. Square that, still 1. We have another 7 down here, so same thing. 5 minus 6 is negative 1. Square that is 1. 8 minus 6 is 2. Square that is 4. So now we're going to add them all up. 9, 10, 11, 12, 16. Finally, we have to divide this by the sample size minus 1, since it's a sample. So it would be 16 divided by 5 minus 1. So this is our sample variance. And to get the standard deviation, that is the square root of the sample variance, so 2. If this was a population, we would divide by 5 instead of 5 minus 1. But since we're told it's a sample, that's all we have there. So now I want to talk about distributions themselves. So here, I have the z-score, wait a moment. So here, let's consider a standard bell curve, because bell curves pop up all the time. Because our bell curve is symmetric, the mean and the median should be about the same, so we just call that mu for the mean. Let's suppose we have 2 data points. We have A, and then we have B. It is reasonable to tell, just from looking at this, that B is not as far away from the mean as A is. However, a question might be, how far away is too far? And we can quantify this with something known as the z-score. And we denote this by z. You can use z, whatever preference you prefer. And the z-score is equal to the data point minus the mean, and that divided by the standard deviation. If we have a sample, we'll have x bar for our mean and s for our sample standard deviation. If we have a population, we will have mu for our population mean and the sigma for our population standard deviation. Now, in these cases, the computations of the z-scores themselves are very straightforward. It's the interpretations of them where it gets interesting. And we have something called Chebyshev's theorem and the empirical rule for understanding these, but it would be more helpful if we actually looked at the 2 broad types of distributions. So here, we can call this a bell curve, but there are other names for it. So this, we can call it symmetric and unimodal, because it's symmetric. Unimodal means 1 peak, also known as a bell. This is also known as a bell curve. It's sometimes referred to as the Gaussian distribution. Most commonly, we call it the normal distribution because it looks normal, as the name implies. Now, sometimes we can have something be symmetric but have more than 1 peak. It could, say, look like this. This would be called bimodal. Bimodal distributions, generally speaking, pop up in nature when you've either messed up and you have 2 completely different samples overlap with each other, or if something more nefarious is at play. We then have what are called asymmetric distributions, and as the name implies, they are not symmetric. So it could look like this, or it could look like this. We could also have it be the other way. It could look like that, or it could look like that. These are all asymmetric. Because there's no vertical line you can draw such that each side would be a mirror of the other. However, we have different ways of describing these types of asymmetric distributions. And for this, we introduce something called skew, S-K-E-W, which represents the direction to which we are skewed. Think of it this way. Let's take a look at this guy. If it wasn't for this goofy looking tail, it would look relatively normal. Since the tail is off on the left side, we say that these two are left skewed, or skewed left. These two, since the tails go off to the right, i.e. the right end is where the goofy stuff is happening, we call these right skewed. So, shorthand, the direction of the goofy tail is the direction of the skew. Now, the thing is, though, let's take a look at these two. For our second one, the skew is not quite as pronounced as with the first one. With this first one, our tail's just going off to nowhere. Whereas our second one, yeah, it's a bit of a goofy looking tail, but not as bad as the other one. So, we call this one significantly skewed. And we call this one slightly skewed. Now you might say, okay, fine, but where's the line? At what point do we go from slightly to significantly? That's a gray area. For the purposes of this class, if there is a skew, it will be very clear if it's significant or not. So for example, I'm not going to give you something that, say, looks like this and say, all right, significant or not. I'm not going to do that to you. If you can correctly identify whether or not there is a skew, then it will be very clear if it's significant or slightly skewed. Essentially, slightly skewed is our tail is a bit further away from the mean, but not too far. And then significantly is our tail is just going off to nowhere. Now, let's talk about the mean, the median, and the modes for these asymmetric distributions. If our distribution is symmetric, then the median is approximately the same as the mean. But if it is asymmetric, the median and the mean will not necessarily be the same. As a side note, all of these, the modes are at the highest points. So now let's think about the medians. If we draw a line here, we still have half the data points to the right. Put another way, these data points could be even goofier. They could be all the way out here. That's not going to touch the median. Put another way, let's suppose we give out a test and we have 3 people that are complete idiots and they're just scoring horribly. If they score twice as worse, that's only going to touch the average and not the median, because the median only cares about the middle or middle 2 data points. Making the extremes even more extreme doesn't touch the median. So in all these cases, our median is still going to be around our peak. It's the mean that changes. So I'll switch to blue to denote the mean. If our tail is skewed to the left, our mean is going to be lower than the median, because now those outliers can significantly impact it, and the similar idea occurs if we're skewed in the other direction. What this means is that the median is not roughly the same as the mean. So, if we have a symmetric distribution, the mean and the median will be approximately the same. If we have a skewed distribution, or an asymmetric distribution, then the mean and the median will not be approximately the same. So now that we've talked about this, let's now go back to those rules of thumb that I was talking about. regardless of whether our distribution is skewed or not, we can still compute z-scores. But the interpretations of those z-scores depend based upon what distribution we're using. So we have what's called Chebyshev's theorem. And if this is kind of hard to read, then it is 1 minus 1 over z squared. That number, by definition, has to be a percentage. The z-score, since it's being squared, cannot be negative. And even if z went up to infinity, 1 minus 1 over infinity would still be a smidge under 1. So this is going to be a percentage. It's got to be from 0 to 1. So that percentage of the data values must be within z standard deviations of the mean. In this case, the z-score we're assuming is greater than 1. Because if it was not, then we'd have more than 100%. It doesn't tell us anything. Now, Chebyshev's theorem works for both symmetric and asymmetric distributions, but it is best for asymmetric distributions because we have something called the empirical rule that is more useful for symmetric distributions, i.e. ones like this bell curve we have here. And this empirical rule states that 68% of the data points are located within 1 standard deviation of the mean, 95% of them are located within 2 standard deviations of the mean, and 99.7% of the data points are within 3 standard deviations of the mean. Now you might ask, where are these numbers coming from? Where does this formula come from? This seems like you're pulling it out of your rump. Kind of, sort of are, kind of, sort of aren't. These numbers, you can rigorously take a normal distribution or an asymmetric distribution and use calculus on them to get these values. And with regards to Chebyshev's theorem, that comes from a Slavic mathematician who, as the theorem would imply, had a last name of Chebyshev's. And given how useful it is, it's only fitting that we name it after him. You'll notice in this course we name quite a few things after the people who discovered them, like with Euler's number, or the Poisson distribution, or sometimes with planets. In fact, the planet Uranus, which makes a lot of school children laugh, they were contemplating naming it after King George, who was the monarch of Great Britain. Yes, back then it was Great Britain and not the United Kingdom, when it was discovered by Herschel. Well, that was his last name. But would be a bit weird to name a planet King George. Nonetheless, we do like naming things after people who discovered them. So, that's why it's called Chebyshev's, and he showed that this holds for all asymmetric distributions within reason. Now, nonetheless, I want to show you some derivations of where these come from and how we can make use of them. So for the empirical rule, you should write down that it is for symmetric only, and best for symmetric, but these numbers, it might be more useful to see them visualized. I have a visual here, but I'm going to remove it and do it from scratch. So, let's suppose we have our normal distribution here, and we have our mean right here. We're going to let red be 1 standard deviation above and below the mean. So 1 standard deviation. We're going to let blue, we'll do green. We're going to let green be 2 standard deviations below the mean. And we're going to let blue be 3 standard deviations above and below the mean. Hey, we're almost halfway to a rainbow. But that is for art class. This is math. This is about as artsy as we're going to get. So, as a side note, let's suppose this data point was 50, the mean was 60, and this standard deviation was 10. Then our z-score would be 50, our data point, minus 60 divided by 10, so -1, which means 1 standard deviation below the mean. Sure enough, that's 1 standard deviation. So that's an explanation of where the z-scores come from. But now let's actually do some work with the empirical rule. The empirical rule says that this is 68% of the data. Well, if it's symmetric, we have to have an even amount on both sides. So this plus this has to be equal to 68. So this must be 34% of the data, and this also must be 34% of the data, because they have to be equal and add up to 68. Okay, now what about 2 standard deviations away from the mean? That must contain 95% of the data. So all of this must be 95%. We have to have the same 95%, well, it has to add up to 95, so we have to have equal amounts on both sides. So 47.5 and 47.5. So 47.5, 47.5. That adds up to 95, and it's symmetric. Well, these two have to add up to 47.5, as do these two. And 13.5 plus 34 is 47.5. So this must be 13.5%, as must this. Now, what these numbers mean, this 34% means that 34% of the data points are within 1 standard deviation below the mean to the mean itself. This 13.5% means that approximately 13.5% of the data points will be within 1 to 2 standard deviations above the mean. Let's now go to our next one. All of this needs to be 99.7%, because according to the empirical rule, 99.7% of the data points are located within 3 standard deviations of the mean. Again, since we have to have an equal amount on both sides, that means we're going to have 49.85 from -3 to 0 standard deviations. Let me make that a bit better. And similar logic from this end, because those two have to be equal to each other because it's symmetric, and it's got to add up to 99.7. Well, if these three have to add up to 49.85, then that means this guy right here must be 2.35%. Same logic holds here. This means that roughly 2.35% of the data points will be within 2 to 3 standard deviations above the mean. Same idea for the lower end. Finally, if this all adds up to 99.7, then that means in our extreme tails, these two have to add up to 0.3%. So therefore these, and I will use purple, are going to be 0.15% each. So this is the graphical display of the empirical rule. So I'll put that up here. Here we go. Graphical display of the empirical rule. I recommend that what you write down is you write down this graph and then also write down 4 symmetric distributions. And then Chebyshev's, you would have 1 minus 1 over z squared for that. Here's why this is more useful than just the straight up definition. If I asked you what percentage of the data points are below 1 standard deviation below the mean, you might not be able to tell that directly from the empirical rule itself. But now that you have this display, you know that all of this is below 1 standard deviation below the mean. So all you got to do is add up those 3 numbers. So 0.15, 2.3, and 13.5, which adds up to 16%. And so you could tell me 16% of the data points are located below 1 standard deviation below the mean, or below a z-score of -1. That's another reason why this display is more helpful. It'll save you a lot of time on the tests as well. So now that I have explained the empirical rule in Chebyshev's theorem, we're going to go over quite a few practice problems with all these distribution shapes and drawing inferences from them. I'll work out the first one, and then y'all will do the other 2. If you want to do all 3, you can go ahead and do that. But otherwise, we're going to get started. So we have a distribution that is known to be significantly skewed to the left. Part A says, what should be used to find what percentages within 1.5 standard deviations of the mean? Chebyshev's empirical rule. Justify your answer. So we're going to use Chebyshev's theorem. Because since it is skewed to the left, it is asymmetric. So Chebyshev's applies. Again, since we're significantly skewed left, it's not symmetric. Chebyshev's is for asymmetric. Now, to actually get it, it is given by 1 minus 1 over our z-score. You might say, what's the z-score? I don't see no damn z-score. Well, we're told it's within 1.5 standard deviations of the mean. The z-score tells you the number of standard deviations away from the mean, so our z-score is 1.5. And we're going to have to square that. Let me zoom in a little bit so I can make it clear. There we go. We're going to square that. And this, you put it into a calculator, you're going to get 5 over 9, or approximately 0.556 if we rounded it. Now our second one. We have a distribution, and it is known to be symmetric and unimodal, so it's a Gaussian distribution. And we're asked, can we use Chebyshev's or the empirical rule? We can technically use both. Chebyshev's, doesn't matter if it's asymmetric or symmetric, it still works. However, the empirical rule will provide the higher estimate and be more reliable. But here, I want to show you why, not just merely say it, but show you. For Chebyshev's, we'd have 1 minus 1 over 2 squared, because if we're 2 standard deviations in the mean, z-score is 2. So 1 minus 1/4, 3/4. So 0, oh, that looks like a 6. So 0.75. The empirical rule, 2 standard deviations of the mean, 95%. Using the graphical display, 34 plus 34 plus 13.5 plus 13.5 is 95. And so here we have 95% or 0.95. This is why we use the empirical rule for the symmetric distribution, because the empirical rule will produce the higher estimate. And since they're both reliable, we take the higher one that gives us more information. Finally, for our last one, I'll have these both here on the same screen so you can see. What percentage of the data is no more than 1 standard deviation above the mean? Well, in this case, no more means less than or equal to 1 standard deviation above the mean. This is our cutoff. So if I zoom in, that's our cutoff. It'll be everything to the left of it. So we're going to add up all these numbers. So for part 1, we'll have 0.15% plus 2.35% plus 13.5% plus 34% plus 34%. So 84%. Now, for part 2, it's saying what percentage is no less than 2 standard deviations below. So here, 2 standard deviations below is here. This is our cutoff. Let me zoom in better. There we go. This is our cutoff, and it says no less than 2 below. So that's going to be all of this. So we're going to add these numbers up. So for 2, we're going to have 13.5% plus 34% plus another 34% plus 13.5% plus 2.35% plus 0.15%, and that all adds up to 97.5%. Finally, we're asked what percentage of the data is between 1 standard deviation below the mean and 2 standard deviations above the mean. So 1 below is right here, 2 above is right here, so we're going to add up the numbers within these two. So 34, 34, and 13.5. So for part 3, we will have 34%, 34%, and 13.5%, which is 81.5%. When it comes to the test and how I will assess you, the only difference between what we've done here is I'll give you some hard numbers. And I'll go ahead and show you a couple of problems with hard numbers so you can get a full idea for it. I'll do one with Chebyshev's. The practice test has one for the empirical rule. So let's suppose, oh my, there we go. Suppose that temperatures in the summer in Lubbock range from 65 to 95 degrees with a standard deviation of say, let's call it 10 degrees. So put another way, suppose that temperatures in the summer in Lubbock have a standard deviation of 10 degrees. The mean temperature is around 80 degrees. So with a mean of 85 degrees. According to Chebyshev's theorem, what percentage of the temperatures will be between 65, I'm sorry, I meant to put 80 here, 65 and 95 degrees. Here we've already done these, doesn't matter. So, in this case, let's go back to red. First of all, we have a mean of 80. So the mean is 80. And our standard deviation, we're told, is 10. So we're asked what percentage of the temperatures will be between 65 and 95 degrees. In this case, our z-score will be 65 minus 80 over 10, which is 1.5, but negative. If you did it from the positive side, you would have 95 minus 80 over 10, which is positive 1.5. However, in this case, because we're going to be squaring it, doesn't matter which one you pick. Chebyshev's states it's going to be 1 minus 1 over z squared. Let's take the negative this time. So 1 minus 1 over 2.25. So it's going to be roughly 55.556%. And so Chebyshev's theorem tells us even if we don't know the distribution of the temperatures, a majority of them should be between 65 and 95 degrees. Now you might say, that's a pile of nonsense. It's going to be more than that. That depends on the month and what it's looking like, say, with El Niño or La Niña. Temperatures in the long run tend to follow a normal distribution, but in the short run, it can depend on the day. We've had summer days where we never get anywhere close to the 90s, and we've had summer days where we go flying past the hundreds. In fact, we've had multiple summers where, say in July, we'll have 3 weeks in a row where it's constantly over 100. So another advantage of Chebyshev's, it doesn't care what the distribution looks like. But otherwise, that's all we have for this back part of Chapter 2. When it comes to your test, you'll do a little bit of calculating standard deviation. You'll have maybe a question or two on that. The preponderance of the questions that I will ask you will deal with applying the empirical rule and Chebyshev's theorem and interpreting distributions with various shapes, which are going to look like one of these. And of course, there is a practice test for the Unit 1 test located inside of the practice test folder within the learning materials folder on Blackboard. This is if you have me, Professor Bailey, as your instructor. If you have a different instructor and you're watching this, it doesn't necessarily apply to you. But for all my students, which is most of you, you can find the practice test in the practice test folder located inside of the learning materials folder. Otherwise, that's all we have for today in this unit. Hope you all have a great rest of your weekend. Stay safe, stay warm.